This is problem 1254. It's on page 527. A curve on a racetrack has a radius of 200 meters and a rated speed of 180 kilometers per hour. Knowing that a race car starts skidding on the curve when traveling at a speed of 320 kilometers per hour, determine A, the banking angle theta, B, the coefficient of static friction between the tires and the track under the current track conditions, and C, the minimum speed at which the same car could negotiate that curve. Neglect any aerodynamic down forces which may act on the car. This is a problem that frequently confuses students. Let me draw several of the views and explain what's going on. First of all, the question is, what is rated speed? Well, if you're looking at a car, say you're looking at oncoming traffic, and this car is going around a curve. Let me sketch the car. There's a racing wheel tire, there's another one, here's the body of the car, here's the cab, there's a little spoiler off the back. Okay, basically this car is going around a curve right now. Okay, it's coming at us at the moment, its tangential velocity is out of this board, but it's going around a curve. So if you were to look at this, let's see, let's put a coordinate system on this from the beginning, and then we'll look at it from another angle. So let's begin with a coordinate system like this, x to the right, y up. Now really x is towards the center of curvature that the car is going around. The car is not increasing its elevation or decreasing its elevation. In other words, it is not moving in the y direction and it's not accelerating in the y direction. But the car is in fact accelerating in the x direction. The way you can see that is to look at this same scene from the top down. So if you were to look at it from this direction, what you would see is the curved track the car is on, and the x-axis would be in this direction. The y-axis we had before would now be out of the page. So if we have a right-handed coordinate system, x into y is z, so basically the velocity is in the z direction. Okay, so right now there's the tangential velocity, and you can see with this center of curvature here, rho, that the car is in fact moving around a corner. And so the acceleration, there's a normal acceleration off to the right. So let's draw it here. So here's a sub n. Let me put rho down here so that we can see it. Okay, so there's a normal acceleration of this car towards the center of curvature, and we'd like to convert this into a free body diagram. Let me change colors, and I will draw the forces acting on this car. At this moment in time, there's of course a normal force in this direction, and there is a weight force that's acting directly down in the, I guess that would be the negative y direction. Now, the initial statement said that the car has a rated speed, or the curve has a rated speed of, let's see, 180 kilometers per hour. What does that mean? Well, what that means is that on this particular curve, if the car is moving 180 kilometers per hour in this direction, there will be no need for friction. In other words, there will be no need for friction up the slope or down the slope. Why? Because the component of the normal force in the x direction is exactly the right amount of force to cause the car to have the normal acceleration an needed at that speed to negotiate this curve. So the road could be slick as ice. It could have absolutely no traction whatsoever, and the car would still make it around the curve, at least theoretically. Okay, so there's a couple of pieces of information that were given that I haven't written down. For example, the radius of curvature is let's see, let's get that right. I think it's 200 actually. The radius of curvature, yeah, 200 meters. And the rated speed, and really this is the speed for part A, the rated speed is 180 kilometers per hour. Okay, so really what we're saying initially is at the rated speed, the friction is zero. So let me just put a frictional force here to begin, and it doesn't matter for now whether it's up the incline or down the incline, because that frictional force will be zero when the car is moving at the rated speed. Okay, so we could sum forces then. If we sum forces in the y direction, basically there's no acceleration in the y direction, so that might make some sense. It might help us out. So let's do that. In the y direction, we have the normal force, and we have some fraction of that normal force. How much? Well, let's see. If we look at this and break up the normal force into its x and y components, we'll need to figure out where the angle theta is located. This line is perpendicular to this one. This line is perpendicular to this one. Therefore, theta is right here. And to get the y component, since that's touching, then I'll have to use cosine. So n cosine theta gives me the y component of the normal force, and that's just balanced by the weight. So this sum is 0 because we know that the car is not accelerating in the y direction. Okay, so if we sum forces in the x direction, then in the x direction, let's see, we don't have any friction force because remember that's 0 for this particular case. The weight only has a y component, so the only x component we get is from the normal force, and so that would be the normal force times the sine of theta equals the mass of the car times the acceleration in the x direction. But in the x direction, the acceleration is just an. So this is just mass times tangential velocity squared over rho. Notice that the x direction is in the same direction as the normal acceleration, so I need a positive sign here. Okay, pardon me. Now the question is to find the angle theta. Sorry. If the rated speed is 180 kilometers per hour. So let's do that. Basically, we have two equations, two unknowns, because we know the speed, we know the radius of curvature. The angle we don't know, the normal force we don't know, and so let's solve for the angle. Anyway, we can rearrange the sum of force equation to say that the normal force would be equal to, let's see, if we move the weight to the other side, make it mg, then we just have to divide by the cosine of theta. So the normal force is just mg cosine theta. And so then, if we put that with the sum of force in x direction, we'd have mg sine theta from here divided by cosine theta, so that we get all of the normal force there. And that's equal to the mass times the tangential velocity squared over rho. You can see that the mass, of course, will cancel out. That's why the curve has a rated speed, the car does not. And so then sine over cosine is just tangent of theta, and so that tells us that theta is the inverse tangent of Vt squared over rho. Okay, so we need the inverse tangent function, and I'm sorry, I forgot the g. The g needs to be divided out as well, so I need a g over here that I missed. Okay, so if you plug all that into your calculator, let me go ahead and do it. Tan theta is tan inverse of 180 kilometers per hour. Of course, we probably should have converted this from the very beginning to meters per second, but I didn't in this solution, so we'll just follow it. Divided by g, 9.81 meters per second squared. Of course, I almost forgot the velocity. Oh, here it is. It's already written the square. And then I have to convert kilometers to meters and hours to seconds. So there's 1,000 meters per kilometer, and there are, well, there's 1 hour per 3,600 seconds, and so that term needs to be squared so that the kilometers per hour squared will cancel with the kilometers per hour squared, and I'll have meters squared per second squared. Pull that down where it should be. There we go. And so anyway, if you plug all that into your calculator, you find that the angle is about 51.8752 degrees if you want that many decimal places. Okay, so there's the angle of the track, and now we know it, so now we can write it down. So let's do that. Theta is 51.8, let me put it down here. In fact, let me just move it over again a bit. That is 51.8752 degrees. So there's the angle of the track, which is a pretty steep track. I mean, if you were going slowly around a track where the angle was over 45 degrees, you would feel very uncomfortable, to say the least. Probably feel uncomfortable at speed as well. But anyway, okay, so that's part A. Part B, they tell us that the skidding velocity, let's change this to part B, we don't have to change a lot. The skidding velocity is twice the rated speed. It's 320 kilometers per hour. Now think about it. If the car is going exceptionally fast, it'll tend to fly off the road in this direction, right? So the frictional force that I have drawn here must be wrong. The car is trying to go up this way, up the incline. So what I should have done for part B is drawn the frictional force down the incline, because if impending motion relative to the track is this way, then the friction is opposite in this way. Now what does that do to our equations? Well, that just changes our force balances a little bit, just adds another term. Because notice the frictional force will have a component in both the x and the y direction. Now another important thing is that at skidding the frictional force will be its maximum. It will be equal to mu n. And so summing forces in the y direction, we'll have to subtract off f sine theta. Let's check that and make sure we're summing forces in the y direction, have a negative y component. Yeah, that makes sense. Now, is it sine or cosine? I'll leave that to you to decide, but you can tell that by looking at the fact that the friction force is at a right angle to the normal force, and therefore to use the opposite sine or cosine. So there's summing forces in the y direction. We know that this is still zero because the car is not moving up or down, nor is it changing its speed in the y direction. So once again, that sum is zero. In the x direction, let's see, there's a positive component of the friction in the x direction, so we have to add f times cosine theta, and that would be equal to the mass times the acceleration in the x direction, which again is just vt squared over rho. So it changes our, the frictional force changes our force balance just a little bit. And so now what we'd like to do is again solve for the unknown. Now the unknown is not the angle anymore. We know the angle of the track. And the question at this point is, if this is close to skidding, then what is the friction coefficient? What is mu? If this is in fact on the verge of sliding, checking the video to make sure that this is still legible. Okay, if it's on the, and by the way, you can download the very sheet that I'm working off of. It's a PDF file in the same learning module, so that's easy to get a hold of in case you can't read anything up here on the board. Okay, so what I'd like to do is somehow solve these equations for the frictional coefficient. Notice this would be a static frictional coefficient because the car is not sliding. So let's see, why don't we just trying to decide if I want to go by my sheet or by this. I'll just go by what I've got on my sheet. So basically from equation 1, which is right here, if we substitute for the frictional force mu n, then what we would have is n cosine theta minus weight less mu n sine theta is 0. Substituting, in fact, let's go ahead and solve for the normal force. There's a normal force here and a normal force here, so basically you take the weight to the other side. Okay, let's just do it. N cosine theta less mu n sine theta equals weight. And then you would take the factors for n out and divide them on the other side. So you would end up with normal force equals weight divided by cosine of theta less mu sine theta. Okay, because those are just the multipliers on the normal force. Now if we take the sum of force in the x direction equation, we can plug in two things. We can plug in the normal force here and we can plug in the friction coefficient here. So if you do that, I'll just do it rather than relying on my sheet. I'm not sure exactly what I did on my sheet, and I want to explain this clearly. So let's plug in the normal force first of all from, the normal force here from here. So we write weight divided by cosine theta less mu sine theta to get the normal force, multiplied by sine theta plus f, but f is mu n. N is again weight divided by cosine theta less mu sine theta Let's see, mu n gives us F let's try this one, times cosine theta, and that's equal to the mass times Vt squared over rho. So let's simplify this just a bit. Weight is just mg. And so the mass will cancel in all of the terms throughout the equation. Once again, mass disappears, which is not really a big surprise. The next thing we need to do is solve for mu. In the interest of time on the video, I'm not going to solve for mu algebraically. It's several steps. You can get it off the PDF. I don't want to waste your time on the video. Let me just show you what you end up with. The static coefficient of friction, and by the way, you should try this too to make sure your algebra skills are up to par. But first thing you should do is divide by g, and I'll go ahead and show you that step. So this is 1, that's 1. You get g over here. That simplifies things a bit. But anyway, solving for mu, v squared divided by rho g cos theta less sine theta divided by, this is all equal, cos theta plus Vt squared over rho g multiplied by sine theta. So, like I said, several steps of algebra to get from this line to this line, but you should try it for yourself and see if you can do it. You should be able to handle that. Okay, so the skidding velocity, if you were to convert that to meters per second, you get 88.8 meters per second as the speed. So now we know the tangential velocity in meters per second. The radius of curvature is still 200 meters, and I forgot my m there. The acceleration of gravity, g, is just 9.81 meters per second squared. We know theta, so everything that in this is a known. And when you plug in all the numbers, like I said, I'll just cut to the chase. This is about 0.449, and it's non-dimensional. So the friction coefficient is about 45%. So 45% of the normal force generates friction to hold the car onto the track. Now, of course, that would change if the speed changed, or if the angle changed. All of those would affect it. Of course, being on Earth would change g versus being on some other planet, and the radius of curvature makes a difference too. But anyway, for our case here, the static coefficient of friction is shown there. So that's part B, and we'll just make a let's make a note of that over here. The friction coefficient mu is 0.449, and it of course is non-dimensional. Now for the last part is basically how slow can you go around this curve, because you can imagine if your car is at not 0, not 45, but 51 degrees, you're not going to feel real comfortable going around this curve, and you might slow down too much. So what would happen? Well, if the car slows down, the minimum speed would be the speed where the car begins to slip down the slope. So basically what would happen is the friction force would change directions, and now it would be up the incline instead of down. And if that happens, what will happen in all of our equations is that the signs will flip on the friction, because now the frictional force is pointing in the opposite direction. So that flips the sign here and here. Let's see, yeah, I'm just solving it here, which will flip the sign on mu there. For this equation, since we now have a negative for the friction coefficient, that flips this sign. And ultimately, what you'll end up with when you solve this, we're no longer solving for the friction coefficient. Now the question is, what's the minimum speed? And so you would solve it out differently. You'd be solving for this. So when you solve and simplify it, I'll skip all the algebra. Basically, well, wait a second, let me check and make sure I've flipped all the signs that I needed to. We were plugging in here, so we plug in the normal force, which is weight, but we moved mg over basically, canceled m, moved g over. Cosine, this should be plus, so that takes care of that term. This should be plus also because we substituted the normal force into the x direction equation twice, and then the minus sign on the friction is reflected there, so that works out. So that should be correct. Let's solve for the velocity. Now this would be the minimum velocity. Because, how do I know it's the minimum? Because, two reasons. The frictional force is now up the incline, which is what would happen if we're going as slow as possible. Also, the frictional force would be at its maximum. Okay? If we're anywhere between the maximum speed and the minimum speed, then the frictional force will not be at the maximum. But anyway, let's solve this out quickly. I'm about out of video time. So this is rho g sine theta less mu cosine theta divided by cosine theta plus mu sine theta. Once again, you should verify that you can reach this with your algebra skills. We know the radius of curvature, 200 meters, g, theta, mu, all these things are now known. When you plug them in, you should get a speed of about 32.09 meters per second, which is about 115.5 kilometers per hour. So there's the minimum speed that the car could use to negotiate the curve without slipping.